Okay, so in this lecture, we are going to do some theory about boosting algorithms. So this is something that I want to talk about today. So the major question that that we always want to ask is, can we using weak learners to combine to and create a strong learners? So use weak learners to create a strong learners. So with that, we already know there are a bunch of methods. We can do bagging, we can do pasting, and we can do random forest. Okay, but let me just do a little bit more methods. So and we want to do something called like an additive models. So and the reason that and with all these three models, we assume say we have using 100 decision trees. Independently. So that means I create 100 trees independently. And to using either random forest, bagging, or pasting, doesn't matter here. But we can make things a little bit better, or like think about it. Can we create a 100 trees sequentially? Sequential and sequential. Why this is important? Because once you create one trees, so you know at a certain point, and this tree can do and can perform and very good in certain area, but it might not perform really good in other areas. So you might be creating another trees on those portion that they make the mistakes the most. So that means if we creating trees and sequentially, so we can ensure we can focus on our method on those like and weak spots. So this is something that is called an additive models. So let me just give like several definition. What is additive and a model? What is the weak learners means? So the weak learner has a definition right here is called um, an algorithm. A is a weak learner. Um, for some space, hypothesis space H, that maps x to y and minus one. If for all distributions over x and any functions little h in big H, that our algorithm A can correctly classify my little h right here at most probability 1 and 1 over 2 minus gamma. So if for all h in and little h and x, our algorithm can correctly classify h with error at most 1/2 minus gamma. So this will be considered weak learner. So we know if the error is precisely equal to half, that would be and then that would be something like no learning at all, because like that would be basically the same as flip coin. But since this is a weak learner, that means it actually still learns something. That means the error that we make is like half minus gamma, which is slightly better than in the random guessing. So let me write out what is the and the sequential, additive and the models and working on. So the setup is the following. Is we have a data. So we are doing classifications. We have a data. We have a data of xi. We have a yi. I from 1 to the n. And also x are in the d dimension, which is we have a d features. And my y is, say, let's just say it's from -1 to 1 again, which is a binary classification problem. So the goal is we want is find some classifier sequentially by t that is something if we input features, it can output my real number r. So you can think about like logistic regressions. So we want to do this sequentially. That means my t has to be from 1, 2 until p, right? So how we find out such kind of classifier? So learn classifiers phi of t. So the way is we want to make sure I have some loss function that between the yi and every ensemble of previously learned classifiers. So sum of t from 1 to big T of my beta t. Let's say t minus 1 here. Wait. Beta t and phi t. Wait. Does it make sense here? Oh, phi t here. So this is my ultimate goal. I want to find out this phi and a phi t such that my loss is minimized. So this will be argue mean of my phi t. So this will be my phi t hat, such that to minimize this whole loss functions. Once we can find out such kind of classifier, then we can make predictions based on our classifiers. So this is my new and a strong classifier and strong learner. So this is I'm going to take, and I want to remind you, this is still the map from R big D to and the little r. Then my fx will just be in the sign of my strong learners. but because it actually maps to the R, so that means if it is positive, I will map into +1. If it is negative, will be and map into like -1. And also we have some weight here, like which is beta t, that we also need to learn as well. Okay. But overall, to find out such kind of like phi t sequentially for phi 1, phi 2, phi 3 until phi big T, that is really, really hard problems. In general, that it's not an easy job. So what we can do is we can like find out our best classifier using forward stepwise modeling. So what is the forward stepwise modeling? That means if I have some like and say some like loss functions already of my big phi, my like classifier and functions and big phi t -1. I'm going to say this is to be applied on x of I. I'm going to add one more correction terms. So this correction terms is called beta t and phi t and x of I. So this is basically one additional terms. I want this whole things to be our new and a new strong classifiers. And this I want this overall, I want this whole thing to have a smaller lost functions from 1 to the n. And of course, I need to make sure this is I have argue mean for the beta t and the phi t. So this is basically the optimization problems that we want to give and solve. And once we can solve our optimal and beta t and phi t, then my next learner, which is my phi t instead of phi t -1, will be phi t -1 plus beta t hat and phi t hat. And that will be like phi t and phi t -1. So that means we add like one additional correction terms to the phi t -1. But in general, this optimization is very hard. That means we usually couldn't do this optimization very well. And if we actually try to do, it might have problem of overfittings as well. So what we can do is we can work on something called an ADA boost. So this ADA boost is saying, I'm not going to find out this optimization problems. Instead, I'm going to propose a way to find out this beta t and phi t's. And later on, I want to argue this beta t and phi t's actually make sense and actually is doing the like goals that we want to do. Okay, so we get around this kind of like optimization problems. Instead of we directly propose and what kind of phi t and beta t's that we're going to use right here. Okay, so this is something called an ADA boost. Okay, so let me just make sure we are in the same page, and make sure I write down all we already know, and what is the goal here. right? So this it's always a good and very important that to make sure you write down your what you already know and what is your goal at any point. So what you want to do is you want to create a strong learner. Construct a strong learner, which is the HX is the linear combinations of phi t. Okay. And we have some like weak learners of phi and phi tx right here. And this right here, phi tx can be like any decision trees, could be like and the logistic regressions. Or like even like simple neural networks. Okay. And also we're enforcing the space. H is the span of the all possible phi tx, which is our hypothesis space. So this is the hypothesis and space that we want to work with. And this phi x is actually some models or some like weak classifiers that we'll be interested in. And of course, I mean, this is, I mean, H is actually giving you an output from R big D into R. It's a real number. It's not, I mean, I'm giving you the predictions. The actual predictions, Fx, is given by taking the sign of Hx. So, I mean, this whole idea is very, very close to the logistic regressions. I mean, if you like know what is the regression, I mean, if you still remember and what is the so logistic regression is right here. Okay, so so let me just write down all these algorithms, and then we're going to talk about step by step and some like logic and some like logic ideas why we want to do this. Then I'm going to demonstrate with one simple examples to see what is this Adaboost is doing right here. Okay, so, and you will see in this Adaboost, we are not actually doing any kind of the optimization directly. In fact, we are trying to minimize this like complicated and very hard optimizations by taking advantage of some aspect that we want to work with. So the algorithm comes with the follows. So the first thing is that you are going to create a uniform vectors. So initialize a uniform vectors, like W1 is equal to like 1 over n. So, and this is some like weight to, and for each point. So this is actually, you can think about as a weight for each training data. So we have n like training data. So that means we are treating each training data equally. So that's why we are getting this like, and like initialize just to consider all the training data have all the equal weight. Then you're going to do this mean training process as the like iteration process. You are going to iterate t times. You can set up the number of t's. You can set it 10, you can set it 100. Depends on how much cost you can afford. All right, so first is you're going to train the classifier like phi t on this training set, on the whole training set D with the weight WT. That actually minimize the weighted error. So what does that actually mean is, this is slightly different way to train and classifiers. We are going to take the whole training data set, but we're going to assign each data set with different weight. That different weight is given by the WT. With that, I want to minimize the weighted error instead, rather than our traditional training error that we treat and each data to be and treat each data to be so uniform. Okay. So then I'm going to compute the weighted training error, which of phi t, which is something called epsilon t, which is summation of my weighted and weighted training errors. Or weighted, it's not training error, it's and weighted accuracies. So whether the yi is not equal to phi t of x of y. So basically, this is weighted training. Still like weighted error, I would say. All right. Then what we do is that is to check with this. So if the epsilon t is bigger than half, then we stop early. So that means we are not improving. If the epsilon is bigger than half, that means our error is actually bigger than random guessing. So we should stop right here. And otherwise we can continue. So there's some like early stoppings that we can put here. Then next is I'm going to change my weight as well. So that means we can see right here, we train our classifier phi t, not directly solving that complicated and optimization problems. Instead, we get around to change the weight of my training data. Then we fit the best phi t's possible. Okay, so this is something that is quite different. Okay, so for that, I'm going to compute my beta t. This beta t is equal to 1/2 logarithm of 1 minus of epsilon t divided by epsilon t. Okay, so you can see this beta t only makes sense when like epsilon t is less equal than half. And otherwise it will be, and it becomes negative, right? So this is something that you need to keep in mind. Then I'm going to update my weight for each training data. So this is, I'm actually the weight for the classifier. So you're going to update the like instances weight. So this will be WT plus 1 of the ith equal to WT of ith exponential minus beta t yi and phi t x of y. Okay, so that means it actually doing some update for my W. Then the D here is we normalize my WT to be T plus 1 to be a distributions, to be a probability distributions. So that means I need to make sure if I sum them and together to be a vector, and the summation should be equal to 1. So this is for just one loop, and we're going to do this for the t times. At the last, this fx will equal to, just take the sign of summations of like 1 to the t of my beta tm and the phi t x. All right, so this is very important. There are a bunch of things that you have to keep in mind. That the beta t right here is to measure the importance of the phi t. So that means if my error is bigger, then my weight should be smaller. If my error is smaller, then the weight is bigger. So my error is smaller. That means I just learned a very good learners. So that means I'm going to have a like higher weight. However, if my epsilon t is bigger, then my beta t and the weight is smaller. Okay, and also my epsilon t is bigger equal than half. As a consequences, is my weight will be strictly bigger equal than 0. Okay, and also you can see right here, I'm going to multiply for each weight by a factor of exponential minus beta t times yi times phi t x of y. So, and you can see if yi and phi t xi is equal to 1, that means either yi or my predictions are both 1, or either one is -1, another one is -1. In any cases, if the multiplication of these two is equal to 1, that indicate I have a correct predictions. And then the weight of multiplication becomes exponential minus beta t, which in this case will be less equal than 1. So and the weight of multiplications will be less than 1. If my yi and phi t of x of y is equal to -1, that means we have incorrect predictions. Then I'm going to multiply that specific point by the weight of exponential of beta t. So that means that in this cases, this will be bigger or equal than 1. So that means if I make correct prediction for this round, then I'm going to shrink my weight for those correct predictions. If I make mistakes on one specific and training data set, then I'm going to make your weight bigger, right? So, and in the next round, I will put more effort to minimize the errors that I make mistakes in the previous round. So you can think about Adaboost is more like way that you collect the and say during your like high school, at each exams, you make mistakes on certain exams, and what you do is you copy down all those problems that you make mistakes. Then you go back and relearn this. Okay, and you put like extra effort on those problems that you make mistakes. Then on the next exams, and you hope if similar problems come back, that you can tackle that kind of the problems easily, since you have put extra effort on those problems that you made mistakes. On the other hand, for those problems you already make a correct predictions, you don't need to go back to review that. So that means proportionally the time that you spend on those problems that you already make correct predictions or made it correct will be less. So you're going to focus on your effort on those incorrect predictions. So naturally, so the question is, how can we come up with this like weighted error? Like for example, what kind of things can naturally put this like and the weighted errors? And for example, with the logistic regressions, there will be some input called sample weight. This is, and you can using this parameter in a passing in with a sample weight. And on the other hand, for example, if you work with the logistic regressions or SVM, you can also like multiply the corresponding weight for each point, then you sum them together. So you can and incorporate this weight into the cost functions. But sometimes they are so there might be some algorithms that we cannot directly support and so these kind of weight. So what we can do is we can using like bootstrap and sampling. So we can perform something like weighted. And bootstrapped. Like sampling. So this is particularly important for those algorithms. There's no natural way that you can do and weighted error. So like such way, you can twitch your training set such that you resample those instances with the replacement, such that all these training sets will be proportionally weight with the distributions of like WTs. So to create a new training set, by resampling. With placement. Okay, so this is very important according to W. Okay, so that means at each round you have to do this bootstrap sampling, such that this, and you create a new training set that with all the the distribution will follow so the probability of the WT. Okay, so let me just show you one like benchmark examples, so you have a good idea what kind of problem and what kind of algorithm that we are working with. Okay, so this is the benchmark examples. Say we have some like points. Right here, we have some like red points, we have some blue points. We want to build a model to distinguish them. And at this point, we assume each ball has the uniform weight. So that means the size actually and represent the weight. And each one has a uniform weight. At round one, I'm going to using some like logistic regressions. So if we're using like logistic regressions, I'm going to draw a line right here to separate blue balls and red balls. But of course, like since these balls is impossible to separate with the linear line, I mean, if we draw this line right here, over here will be predict as a red balls. Over here will be predict as a blue balls. So we can see for these two balls was supposed to be red, but was predicted as blue. So these two balls are the mistake ones. Same right here. So these two balls should be blue, but predict as red. So then what we do is in the next is I'm going to change the weight for each of balls. So that means for those balls, we make the correct predictions that I'm going to proportionally shrink the weight by a little bit. On the other hand, for those balls that we make mistakes for, and for example, for these four balls, I'm going to proportionally increase the weight and a little bit for the next round, such that for the next round, I want the next round predictors put emphasis on these four balls, such that hopefully the next round they can make better predictions for those four balls. Okay, so so that would be my new training data set because my weight is different. And although the position of my training data set right now is the same, but my weight is different. So my loss will be different as well. So that means for the next round, you will be getting this training data set. You're going to draw and do this like logistic regression again. But on the other hand, on this time, we are drawing the line right here, and everything here will be predicted as blue, and everything here will be predicted as a red. So we can see all these 3 points is actually give the correct predictions. And all these blue points is actually giving you the correct predictions. However, for these 3 balls, actually we make mistakes. So that means I'm going to multiply some like certain weight to make these three balls bigger. So you can see right here, these three balls is getting bigger. On the other hand, every other balls, I'm going to shrink it by certain constant. Okay, so this is the weight after the second round. So we do the same things for the third round right here. Then we continue for the fourth round. And you can see because we change the weight consistently, the loss function is different. As this result, my line and my logistic regression will be completely different. Just because of the reason that we have right here. So we continue doing this until the t. T could be like 15 or 20s, depends on what you want. You can see we draw so many different lines right here. And it's all around the whole space. Then we can make this predictions with like and linear combinations for those classifier from phi 1 to phi t. And actually, we can build the boundary conditions directly. And you will find that it actually gives you the boundary conditions very nicely, like that. And with this and a linear combination of all these and the logistic regressions, turns out that we can create a nonlinear boundaries on the whole spaces right here. It actually predict everything inside will be blue and everything outside will be red, which you can see it perfectly separate these two balls very nicely and without giving you out much zigzags. So that means if we make these predictions with that kind of like decision boundaries, it actually shows it might not have much overfitting issues. It actually made a very perfect jobs for that. Okay. So this is some examples that you can see right here. So we can run this whole thing. So this is again my my moon. So moon shape and a data set. We create an ADA boost with the decision trees, but we specify our decision trees. We only have maximum depth is equal to 1. We only have a 1 layer of the decision trees. It's super simple one. So I'm going to create number of the estimator. So that means I'm going to create 30 trees, t equal to 30. Some learning rate. So that means there's something that you need to twitch of the like and the proportional of my so my weight changes. And with that, you will find out it actually did pretty good job getting 91.2 of accuracies. 90 and 90% and of the accuracies, right? So so it actually give you a pretty good results. So this is very powerful and ensemble techniques. Sometimes it's doing better than random forest with the same number of the trees. And also you don't need to tune much parameter for the ADA boost. Except for those like T's that you want to choose. And also you need to change your some parameter for the base learners. But usually the base learner could be super weak, like these kind of decision trees with 1 layers. That would be super weak learners. But that will be sufficient. There's not much like a parameter you need to tune. Just pick your T, and you are good to go. So it's very good, and it's very effective because it will focus, trying to train your models, focusing on those points that you make mistakes. But there's a very important disadvantage of this ADA boost, that this boosting algorithm is actually sequential. So that means these trees cannot be trained in parallel. So you actually have to train the first one, or the first, and the result from first one, then you can train the second one. With the result of first one and second one, they can train the third ones and so on. So you cannot train those like 20 trees in parallel in 20 different cores. So this is a major issue here on Adaboost. On the other hand, if you want to work with random forest, and you can have a 100 trees, and these 100 trees can be trained in parallel. So it's not a problem. It's always possible to train them in parallel. So this is very important nowadays because you can have hundreds, 20s, and hundreds, 200s, even thousands like cores and working for you. Or even you can take advantage of GPUs. And then, the more cores that you have, then the faster of the algorithm that you have. And you also need to consider the running time as well. And then with that, this Adaboost, it will not have that kind of powerful in situations because you cannot choose your T's to be very large, right? If you choose your T to be very large and you want to work on a very large data set, as a result, you can only work on using one CPU cores, and then that would take forever. So on the contrary, if you're working with the random forest, you can put all these problems and distribute these problems into hundreds or even thousands cores. So this will be much more efficient. All right, so and you can also do this ADA regression as well, which is very similar to Adaboost. And you can see this whole algorithm is very close to what we have. But the difference is right here is, instead of we using the weighted and error right here, like this, weighted error here, because this is actually, we're trying to count how many errors. And so when we have the error, then we multiply the weight. All right, so with that, in fact, we can using other type of errors right here. We can, and for example, we can using this absolute error because we are doing and regressions, and the possible choice of the errors actually matters. And of course you can choose the square errors, and you can choose the absolute errors. So these will be this will be extremely important. And of course, you can choosing the maximum error as well. So either one will be fine. So everything else will be basically the same. So the notation is slightly different, but the whole idea is basically the same. We still need to check whether sorry, I think this one we still need to check whether my error right here, training error is bigger than half or not. Because if it is bigger than half, then my wait, let me think about this. Oh yeah, we don't need to do that because this is not a classification problem. We don't need to check whether my error is bigger than half or smaller than half. So in Adaboost regression, they will not be having some early stoppings, and because we can always have some training error, could be large, could be small, it doesn't matter. You just need to and update the weight correspondingly to reflect and how good my classifiers is doing right here. Okay, so everything will be the same. Just the difference is how we choose the errors right here. Okay, so it's usually an Adaboost is very and works very well, but sometimes it will have overfittings because you might run into too many T's and you don't know what is the optimal T's that you should be choosing here. But if you choose too many T's, you might overfit. It's very likely that you will have problems. In fact, these overfitting problems indeed exist. I mean, especially when your data has a lot of outliers. I mean, if your data has a lot of outliers, then your Adaboost will not be stable, and then that will have problems. Okay, so that's one of another disadvantage of my and of the Adaboost problem and algorithms. And then this is also commonly asked questions during interviews, and when this Adaboost will fail. In fact, the Adaboost will likely fail if you have some very strong outliers. Then you have a problem. Okay, so this is the first part of the video. I'm going to continue on the second part on the gradient boostings.